Okay, guys, so today we're going to be talking about periodic trends, trends within the periodic table among the properties that some of them we've discussed a little bit, like the atomic radius, electronegativity, ionization energy, things like that. We're going to explain them in more detail later on. We just kind of mentioned them with respect to how Mendeleev designed the periodic table. So we can explain all periodic trends that we're going to be discussing, and there will be three of them, looking at by first looking at something called effective nuclear charge. So what is effective nuclear charge? Effective nuclear charge, or ENC, um, is the push and pull felt by valence electrons. So the electrons of the outermost energy level of an atom. That's what effective nuclear charge refers to. So for example, if I start very simply, let's say we're talking about lithium. Lithium, Li, has atomic number 3, so it's got a positive 3 charge in the nucleus. Let's say that's the nucleus. And then if you look at the periodic table, lithium has, it starts with 1s2, so it has 2 electrons in the first energy level. And notice for this, we're just looking at a Bohr model, just where are the electrons. So 2 in the first energy level, and then that leaves one more electron that's going to be out here in the second energy level. So it's out here in the 2s, so it's 2s1 that it ends with. So when we say what is the effective nuclear charge for lithium, what we're saying is what is the push and pull felt by that electron out there in the valence energy level. Okay, so how do we figure that out? Well, what's pushing it and what's pulling it? Let's start with the pull. For lithium, we have to remember, or for any element, we have to remember that that electron is negative. Okay, so it's going to be pulled or attracted to the positive nucleus. So for that electron to describe how much pull it's feeling towards the center of the atom, we would say that that pull is 3. You could put a positive sign in front if you want to. But what we're going to then do is subtract the push or repulsion. And what that means is there's something else in the atom that's pushing that electron away, okay? And that, of course, would be these other electrons that are in the inner shells. In this case, there's only 2 shells or 2 energy levels for lithium, but there are 2 electrons in the inner shell for lithium that would be repelling because opposite charges attract, but like charges repel. So that valence electron is being pushed away, and we do pull minus push by 2 electrons. And the result of that would be positive 1, right? So we would say the effective nuclear charge, the pull minus the push, equals ENC, which in this case would be 1. Okay? So hopefully that makes a little bit of sense. So what these numbers are is this is the number of protons, so I'm going to say number of P plus, and this is the number of inner shell electrons. In other words, the electrons that are not out there in the valence energy level. Okay, so let's talk about and bring in another element from that from the same period or horizontal row as lithium. So here's lithium. Let's talk about beryllium. Okay, beryllium is atomic number 4. So that means it has 4 protons, and it also, assuming it's neutral, has 4 electrons. So let's say I want to draw beryllium. So Be is going to have a nucleus with a positive charge of +4. All right, it's going to have, similar to lithium, it's going to have 2 electrons in its first energy level. And then it's going to have, this time, instead of just 1 in the second, it's going to have 2 in the second. Okay. Now, let's think about how we would calculate its effective nuclear charge and then what that means. So what we do is we just pick one of these 2 valence electrons at random, it doesn't matter which one, and we describe the pull and the push. So the pull, in this case, would be 4, because this time the nucleus has 4 positive protons instead of just 3 like lithium. So that's the pull being felt by that valence electron. Then the push that we're going to subtract is the same as it was for lithium. So it's 2. And what that, all I'm saying there is, just like with lithium, it has 2 what we call inner shell electrons. So it's being pulled in with a positive 4 nucleus, or by a positive 4 nucleus, and repelled or pushed away still by just 2 inner shell electrons. Okay? And so that gives us an effective nuclear charge of 4 minus 2, which would be 2, right? So an effective nuclear charge of 2, right? Okay, so what does that mean? Well, it means something very important for our periodic trends. The first thing it means is that beryllium, even though it is a heavier element, you would assume that it would have a larger radius. But it doesn't. And the reason is the effective nuclear charge, the positive 4 nucleus specifically, is pulling in those valence electrons with more attraction, more positive charge, more force. And that's going to actually make a beryllium atom, even though it's heavier than a lithium atom, it's going to make a beryllium atom smaller in terms of its radius or its size. And actually this trend continues, because if we look across the rest of the second period, from lithium to beryllium to boron, carbon, nitrogen, we just keep getting smaller. And the reason is, for all elements of the second period, they just have 2 inner shell electrons. Those would be in the case of the second period elements, those would just be the 2 electrons in the first energy level, shielding or pushing those valence electrons away. But the nucleus is getting more and more positive, from 3 to 4 to 5 to 6, all the way up to neon, which would be 10. So if we looked at a neon atom and talked about, okay, why is a neon atom smaller than a lithium or a beryllium? Because it's so much bigger. Well, a neon atom is going to have a positive 10 nucleus. It's a lot more positive, right? Now, its inner shell is still just going to be 2 electrons. Now, it has a bunch of valence electrons. It has 8, so basically 2s2, 2p6. So I'll go ahead and put in 4, 6, 8, okay? So when we talk about effective nuclear charge for an element, we're simply talking about the pull, which in the case of neon, which would be, in the case of neon, that would be 10. Okay, so the pull would be 10 positive protons, but we're still just subtracting 2. Okay, and you might be thinking, well, why? We have all these electrons. How come it's only got 2 electrons repelling the valence electron? Well, again, we're only talking about one of these valence electrons. Let me just say, I'll highlight this one and say that's the one I'm talking about. All of these other valence electrons out here in that second energy level are on the same energy level as the one that I'm talking about. It's only these 2 electrons in the lower energy level that are between my valence electron and the nucleus, shielding or pushing, repelling that electron away from the nucleus. So the push, the repulsion, is still just 2, and that would be the case all the way across that second period of the periodic table. So we are going to have a huge effective nuclear charge of 8, because I do 10 minus 2, and therefore, with all of that positivity, all of those positive protons, 10 of them, pulling the valence electrons in close, and not any more shielding or repulsion, pushing them back out away from the nucleus, that neon atom becomes very small compared to the things in the same period but further to the left. And then the next thing we're going to talk about tomorrow, actually, is what does this have to do with the trends? What does this have to do with the radius, which we kind of just talked about, ionization energy, and electronegativity of the atoms, not only within a period, but also, up and down within a group.